Example 17.12. In this example, aluminum pin fins of parabolic profiles with blunt tips are attached to a plain wall with a surface temperature of 200 Celsius. Each fin has a length of 20 millimeters and a base diameter of 5 millimeters. The fins are exposed to an ambient temperature of 25 Celsius and a convection heat transfer coefficient of 50 watts per meter square per Kelvin. If the thermal conductivity of each fin is 240 watts per meter Kelvin, we need to determine the efficiency, the heat transfer rate, and the effectiveness for each fin. To solve this problem, we're going to assume steady state conditions, treat the fin to be one-dimensional, and we're going to have constant properties. In order to solve this problem, we're going to use tables that are in your textbook. The number of the tables may be different in different editions. However, the content will be basically the same. And even other textbooks that you may use, the resources will be exactly the same. So notice that we'll look, in this case, we look for table 17.3. It has different fins with different shapes, and it provides the information that we need for those fins. For the one that we're looking for is a parabolic profile with a blunt tip, and basically this is the case that we're looking for. Okay, so notice that we have certain information. We have the value of m, which is used in most of the equations. We also have the area of the fin, and we have the efficiency. Okay, so let's just start with the value of m, and notice that most of the values that we're going to use is m times L, so we're going to calculate that, m times L. And we're going to use the equation that is provided, which is 4h over kd, and we multiply that by L. We substitute all the values that we get, and we find that this constant is equal to 0.2582. And if you did your units properly, you're going to find that it is a unitless or dimensionless quantity. The second thing that we're going to calculate is the area of the fin. So I am not going to substitute into that formula, but what we're going to see is once we substitute all the values, you're going to get 2.106 times 10 to the negative 4 meters square. And be careful when you do these calculations. Notice that it has fractions in the exponent, so very careful when you substitute. Then now we're going to go to the interesting component. We're going to go to the efficiency. And when we look at the efficiency, notice that what we have to calculate is I1 and I0. Those are known as the modified Bessel functions of different kinds. And notice that what we need to calculate is the value of 4ml over 3. So we need that constant before we start. So we have 4m times L divided by 3. We substitute the value that we got for m times L, and we see that that constant is equal to 0.3443. Okay, so that is the value that is inside of the modified Bessel function, which, looking at your table, in this case 17.4, corresponds to the value of x. So now we need to interpolate. The interpolation that we're going to do is going to be between 0.2 and 0.4, since the value that we're looking for is in between those two. Okay, so I'm going to show you how to solve for I0, and then you could do the second part. So we have x, and we see that we got 0.2, 0.4, and 0.3443. And notice the title that you have in your column where you're looking for is e to the negative x, I0 to the x. And the corresponding values that we have are 0.8269, 0.6974. And if we do a linear interpolation using those values, we find that the corresponding value for this is 0.7334. Now this value is equal to e to the negative 0.3443 times I0 of 0.3443. And remember, what we're looking for is the value of the modified function, which is this. So that means in order to get it, we have to divide both sides by e to the negative 0.3443 to be able to get the value for that. And after we do that division, we find that the modified Bessel function for the corresponding value, it gives us 1.035. If you do the same process for I1, we find that the value of I1 simply becomes 0.1716. And that's basically the most complicated part of this problem. Once you have the value of I0 and I1, you will be able to substitute it into this equation over here. Okay, so now we're gonna substitute into that formula. We find that the efficiency of a fin is equal to 2 ml I1 of 4 ml over 3, which we already found, and I0 4 ml over 3. So we substitute the values that we have. We got 3 over 2, the value of ml, it was 0.2582, and we already find the values. I1 is 0.1716, and the value of I0 is 1.035, and then we find that this efficiency is equal to 0.9632. The next part of your problem is to find the heat transfer rate of this fin, and that is provided simply by Q of the fin is equal to the efficiency of the fin times H, area of the fin, and the change in the temperature between the base and the ambient. Okay, so we have all the information. This is 0.9632. We have that the value of H given by the problem is 50 watts meter square Kelvin. The area of the fin was calculated to be 2.106 times 10 to the negative 4 meters square, and the change in temperature goes from 200 to 25 Celsius, and we calculate all this value, we get 1.77 watts. Okay, so we have all the information for the heat transfer rate. The next step that we need to calculate is the value of the effectiveness of the fin. Okay, so we're gonna do it over here. The effectiveness of the fin is going to be equal to the heat transfer that we calculated of the fin divided by the maximum amount that we will have if we didn't have the fin. So H, the area of the base, TB minus T infinity. Okay, so we substitute the values that we have over here. So we have Q of the fin, we calculated already to be 1.77 watts, and H we have 50 watts per meter square Kelvin. The area of the base is a circle, so it's pi over 4. The diameter is 5 millimeters, so it's 5 to the negative 3 square. This is meters. And then we have again the change in the temperature. We have 200 minus 25 Celsius, and we calculate, and it gives us a value of 10.3. Okay, so let's recall the difference between effectiveness and efficiency. Effectiveness tells us whether or not we should add the fin into the system. We want a number at least 2 or greater. So the fact that we have a 10, it tells us that this basically behaves better 10 times, at least 10 times better as if we didn't have the fin. Also notice that the efficiency, once we install the fin, tells us how well that fin is working, and it goes from 0 to 1, and in this case we got an efficiency of 96%, which means that is a very good fin. And each one of the fins is going to be able to have a heat transfer of 1.77 watts.